In earlier videos, I've said over and over that when you're developing a machine learning system, one of the most valuable resources is your time as the developer in terms of picking what to work on next. Or if you have a team of developers or a team of engineers working together on a machine learning system, again, one of the most valuable resources is the time of the engineers or the developers working on the system. And what you really want to avoid is if you or your colleagues, your friends spend a lot of time working on some component only to realize after weeks or months of time spent that all that work just doesn't make a huge difference on the performance of the final system. In this video, what I'd like to do is talk about something called ceiling analysis. When you have a team working on a pipeline machine learning system, this can sometimes give you a very strong signal, a very strong guidance on what parts of the pipeline might be the best use of your time to work on. To talk about ceiling analysis, I'm going to keep on using the example of the photo OCR pipeline. And as said earlier, each of these boxes, text detection, character segmentation, character recognition, each of these boxes can have even a small engineering team working on it, or maybe the entire system is just built by you, either way. But the question is, where should you allocate resources? And which of these boxes is most worth your effort trying to improve the performance of? In order to explain the idea of ceiling analysis, I'm going to keep using the example of our photo OCR pipeline. As I mentioned earlier, each of these boxes here, each of these machine learning components could be the work of even a small team of engineers, or maybe it could be the whole system could be built by just one person. But the question is, where should you allocate scarce resources? That is, which of these components, or which one or two, or maybe all three of these components is most worth your time to try to improve the performance of? So here's the idea of ceiling analysis. As in the development process for other machine learning systems as well, in order to make decisions on what to do for developing the system is going to be very helpful to have a single row number evaluation metric for this learning system. So let's say we pick character level accuracy. So given a test set image, what is the fraction of alphabets of characters in the test set image that we recognize correctly? Or you can pick some other single row number evaluation metric if you want, but let's say that for whatever evaluation metric we pick, we get that we find that the overall system currently has 72% accuracy. So in other words, we have some set of test set images, and for each test set images, we run it through text detection, then character segmentation, then character recognition, and we find that on our test set, the overall accuracy of the entire system was 72% on whatever metric you chose. Now, here's the idea behind ceiling analysis, which is that we're going to go to, let's say, the first module of our machine learning pipeline, say text detection. And what we're going to do is we're going to monkey around with the test set. We're going to go to the test set, and for every test example, we're just going to provide it the correct text detection outputs. Right? So in other words, we're going to go to the test set and just manually tell the algorithm where the text is in each of the test examples. So in other words, it's going to simulate what happens if we have a text detection system with 100% accuracy for the purpose of detecting text in an image. And really, the way you do that is pretty simple, right? Instead of letting your learning algorithm detect the text in the images, you would instead go to the images and just manually label what is the location of the text in my test set image, and you would then let these correct or let these ground truth labels of where is the text be part of your test set, and just use these ground truth labels as what you feed in to the next stage of the pipeline, to the character segmentation pipeline. Okay, so just to say that again, by putting a check mark over here, what I mean is I'm going to go to my test set and just give it the correct answers, give it the correct labels for the text detection part of the pipeline. So that is as if I have a perfect text detection system on my test set. What we're going to do then is run this data through the rest of the pipeline, through character segmentation and character recognition, and then use the same evaluation metric as before to measure what is the overall accuracy of the entire system. And with perfect text detection, hopefully the performance will go up, and in this example, let's say it goes up 89%. And then we're going to keep going. Next, let's go to the next stage of the pipeline, to character segmentation. So again, I'm going to go to my test set, and now I'm going to give it the correct text detection output and give it the correct character segmentation output. So let's go to the test set and manually label the correct segmentations of the text into individual characters and see how much that helps. And let's say it goes up to 90% accuracy for the overall system, right? So as always, the accuracy is the accuracy of the overall system. So whatever the final output of the character recognition system is, whatever the final output of the overall pipeline is, going to measure the accuracy of that. And then finally, I'm going to go to the character recognition system and give that the correct labels as well. And if I do that too, then no surprise, I should get 100% accuracy. Now, the nice thing about having done this analysis is we can now understand what is the potential upside, the upside potential for improving each of these components. So we see that if we get perfect text detection, our performance went up from 72 to 89%. So that's a 17% performance gain. So this means that if we take a current system and we spend a lot of time improving text detection, that means that we could potentially improve our system's performance by 17%. It seems like it's well worth our while. Whereas in contrast, when going from text detection, when we gave it perfect character segmentation, performance went up only by 1%. So that's a more sobering message. It means that no matter how much time you spend on character segmentation, maybe the upside potential is going to be pretty small, and maybe you do not want to have a large team of engineers working on character segmentation if this sort of analysis shows that even when you give it the perfect character segmentations, your performance goes up by only 1%. So that really estimates what is the ceiling or what's an upper bound on how much you can improve the performance of your system by working on one of these components. And then finally, going from character, when we get better character recognition, the performance went up by 10%. So, again, you have to decide, is a 10% improvement, how much is that worth your while? But this tells you that maybe with more effort spent on the last stage of the pipeline, you can improve the system. You can improve the performance of the systems as well. Another way of thinking about this is that by going through this sort of analysis, you're trying to figure out, what is the upside potential of improving each of these components, or how much could you possibly gain if one of these components became absolutely perfect, and this really places an upper bound on the performance of that system. So the idea of ceiling analysis is pretty important. Let me just illustrate this idea again, but with a different example of a more complex one. Let's say that you want to do face recognition from images. So let's say you want to look at the picture and recognize, whether or not the person in this picture is a particular friend of yours, or try to recognize the person shown in this image. This is a slightly artificial example. This isn't actually how face recognition is done in practice, but I want to step through an example of what a pipeline might look like to give you another example of how a ceiling analysis process might look. So we have a camera image, and let's say that we design a pipeline as follows. Let's say the first thing you want to do is do pre-processing of the image. So let's take this image like I have shown on the upper right, and let's say we want to remove the background. So do pre-processing, the background disappears. Next, we want to, say, detect the face of the person. That's usually done with a learning algorithm. So we'll run a sliding windows classifier to draw a box around the person's face. Having detected the face, it turns out that if you want to recognize people, it turns out that the eyes is a highly useful cue. We actually, in terms of recognizing your friends, the appearance of their eyes is actually one of the most important cues that you use. So let's run another classifier to detect the eyes of the person. So segment out the eyes, and then since this will give us useful features to recognize the person, and then other parts of the face, the particular interest, maybe segment out the nose, segment out the mouth, and then having found the eyes, the nose, and the mouth, all of these give us useful features to maybe feed in to a logistic regression classifier, and it's the job of the classifier to then give us the overall label, the final label for who we think is the identity of this person. So this is a kind of complicated pipeline. It's actually probably more complicated than you should be using if you actually want to recognize people. But there's an illustrative example that's useful to think about for ceiling analysis. So how do we go through ceiling analysis for this pipeline? Well, we'll step through these pieces one at a time. Let's say your overall system has 85% accuracy. The first thing I do is go to my test set and manually give it the ground truth foreground background segmentation. So manually go to the test set and use Photoshop or something to just tell it where's the background, and just manually remove the background, so this is the ground truth background, and see how much the accuracy changes. In this example, the accuracy goes up by 0.1%. So this is a strong sign that even if you had perfect background segmentation, your performance, even if perfect background removal, the performance of your system isn't going to go up that much. So it's maybe not worth a huge effort to work on pre-processing, on background removal. Then we can go to the test set, give it the correct face detection images. Then again, step through the eyes, nose, mouth segmentation in some order. Just pick one order. Let's give the correct location of the eyes, correct location of the noses, correct location of the mouth. And then finally, if I just give it the correct overall label, I get 100% accuracy. And so, as I go through the system and just give more and more components the correct labels in the test set, the performance of the overall system goes up, and you can look at how much the performance went up on different steps. So, from giving it the perfect face detection, it looks like the overall performance of the system went up by 5.9%. So that's a pretty big jump. It means that maybe it's worth quite a bit of effort on better face detection. Went up 4% there, it went up 1% there, 1% there, and 3% there. So it looks like the components that are most worth our while are when I gave it perfect face segmentation, face detection, system went up by 5.9 performance. When I gave it perfect eye segmentation, it went up by 4%, and then my final logistic classifier, well, there's another 3% gap there maybe. And so this tells us maybe what are the components that are most worth our while working on. And by the way, I want to tell you a sort of true cautionary story. The reason I put in this pre-processing background removal is because I actually know of a true story where there was a research team that actually literally had 2 people spend about 1.5 years, spend 18 months working on better background removal. They're actually, I'm obscuring the details for obvious reasons, but there was a computer vision application where there was actually a team of 2 engineers that literally spent, I think, about 1.5 years working on better background removal. Actually worked out really complicated algorithms, so I ended up, I think, publishing 1 research paper. But after all that work, they found that it just did not make a huge difference to the overall performance of the actual application they were working on. And if only someone were to do a ceiling analysis beforehand, maybe could have realized this. And one of them said to me afterward, if only they'd done a sort of analysis like this, maybe they could have realized before that 18 months of work that they should have spent their effort focusing on some different component than literally spending 18 months working on background removal. So to summarize, pipelines are pretty pervasive in complex machine learning applications. And when you're working on a big machine learning application, I think your time as a developer is so valuable. So just don't waste your time working on something that ultimately isn't going to matter. And in this video, we talked about this idea of ceiling analysis, which I've often found to be a very good tool for identifying the component that if you actually put a focus effort on that component and make a big difference, it will actually have a huge effect on the overall performance of your final system. So over the years, working in machine learning, I've actually learned to not trust my own gut feeling about what component to work on. So very often, I've worked on machine learning for a long time, but often I'll look at a machine learning problem and I may have some gut feeling about, oh, let's jump on that component and just spend a lot of time on that. But over the years, I've come to even trust my own gut feelings, or learn not to trust gut feelings that much. And instead, if you have a sort of machine learning problem where it's possible to structure things, to do a ceiling analysis, often that's a much better and much more reliable way for deciding where to put a focus effort to really improve the performance of some component, and be kind of reassured that when you do that, it will actually have a huge effect on the final performance of your overall system.